To get a full learning experience from this webcast, pause and play each segment. Use this webcast to pace the mathematical activity of your study group. Engage in the mathematical work and discussion as prompted throughout this webcast, and discuss your study group's responses. Keep a jot-note journal of your mathematical thinking and your thinking about mathematics instruction throughout this webcast.
Welcome to Literacy and Numeracy Secretariat's February webcast entitled High-Yield Strategies for Improving Mathematics Instruction and Student Learning. We are pleased to have you join a mathematics study group comprised of grade 6 teachers, principal, vice principals, and program consultants from the Ottawa region. During their study sessions, they solved and discussed math problems they would be using during their numeracy learning blocks, and they analyzed and described the range of mathematics inherent in solutions to such problems. Also, they were learning to use different instructional strategies to make explicit, consolidate, to extend student learning, as well as to improve the clarity and precision of students' mathematical communication.
Each of them are half, and half plus half equals 1 in square unit. And there's also another 2 halves there, and two halves equal 1 square unit. We measured the criteria for at least 4 square units.
Here I just started with the parallelogram and put like 2 triangles on it to make it a rectangle. And I did put a square there, and that like covered everything.
Okay.
And like, yeah, I did like the same thing here, but I turned it around so it was like different.
Okay, so basically, these are both good, but with the small one, I think that it might have, like with Breyer's, it's the exact same type of like form. It's just that yours is like split up into more sections, so it might be a little bit confusing to other people.
I think this is you're not quite sure with that one, and then you can have a fun decision.
Are you making okay, so I'll write a math set.
Why don't you use
half and half is 1 square unit, and we know that, so that times 4, 1, 2, 3, 4.
1 rectangle, C, and 1 parallelogram, which is E. So we have all 3 puzzle pieces that must be included. A right angle triangle has a base and a height, and it would be easier to find instead of searching for the height. It was right there for us.
Berto, you want to do area C?
And then 2 arrows on this side.
Berto, just come on the side of Taylor and do area.
Our calculations were
You can point.
base times height divided by 2, and the dimensions were 2 centimeters by 6 centimeters
Okay. Which gave you an answer?
of 12 centimeters squared, and then we had to divide it by 2 to get our answer of 6 centimeters squared.
We know the formula is base times height. So the base was 4 units times the height, which was 4 units also. So that would be 16 units square. And then since it was there's only one parallelogram, we don't have to multiply it by 2.
I'm wondering about a couple of things with regard to mathematical communication. The role of the community, the role of your classroom community for mathematical communication. What impact does that have on students expressing their mathematical ideas? And I'm also wondering about the activities or the tasks, more specifically the problems that students are given to work on in class. What's the impact of the problem that students are given on their communication, on their mathematical communication?
I'm wondering how we can move away from the narrative explanation of their thinking to more of just a presentation of their thinking using the symbols and not just always focusing on a picture and number and words. So, you know, I was talking to my students yesterday and they were saying, I don't have enough room to explain everything I was doing. I said, well, you know what? The clearer you make this, the more proof you've given me. I don't need a story. I don't need step 1, step 2. Like Sonia, you were saying, move away from the steps. It's very restrictive. So I think the more we move away from the steps and the more we move away from the narrative, they'll feel more comfortable to explain their thinking using symbols and like accurate symbols and pointing using accurate vocabulary and terminology.
I'm wondering how we can get students to actually value that precision is important and being clear and accurate is important.
I wonder how we can get students to think critically about what is the best way to communicate their solution. So is it better at this point to use words or symbols, and how will each impact on my community's understanding of my solution?
And I'm wondering how we can encourage students to connect those two pieces so that their arguments are more convincing.
And meaningful.
And meaningful.
And it also is hard to know as teachers how you can get around to each group so that you have evidence of their oral communication. When you have a junior class with 6 or 7 groups of students, how you get around to each group of students to clearly understand what it is they're trying to tell you and relay in their information, and to be able to probe them a little further and ask those deeper questions so that they can continue on their learning. How do you do that as a classroom teacher when you're the only person in the room?
I'm wondering what assessment tool we could use as teachers that we could accurately gather, information about the children's math communication as well as their math thinking, being one teacher, as you said, in the room.
So when we started our study group, we knew what we wanted to focus on based on our data, and we chose some expectations from the measurement unit. And now we have done some work with our students. We're going to look again at our expectations to see where we are and to make adjustments to our plan, because based on students' work, we may decide to go in a slightly different direction. So the curriculum is going to help us in focusing our next steps.
Our goals for today are to continue our exploration of mathematical communication. We'll be looking at how we can use problems in math class to elicit students' communication about their reasoning and their justifying of their solutions. And we're also going to look at some assessment criteria for mathematical communication. So you ready to go? Okay. I've got an activating problem for you to just contemplate. I don't think it's in its finished form yet. So this is the problem right here. What does a square, triangle, and parallelogram each look like that is 4 square units? Show your work. So this problem would be given at the outset of the lesson for students to kind of engage in the mathematics. Do you have any comments about this? Any suggestions?
Let's try it.
Let's try it then. Okay, let's go ahead and try it.
Way.
It's worth they can finish off in short.
Yeah.
What do you think, Sonia? She's been so flexible.
How long would it take? 20 minutes? I'll come out at
It's the one that 3 of you here.
Also, too, when you're describing your solution,
you want to change the wording of the problem.
Yeah, just put rectangle instead. Okay. I think that some students, if they get the relationship between triangle and rectangle, if they need a triangle that's 4 square units, they might start by drawing a rectangle that's 8 square units. And once you do that, you can make any size triangle inside with the base and height.
I think they're actually just focusing on like a polygon right now. They haven't come back to the vocabulary and the meaning of parallelogram.
And the composite shapes. I think they're putting them together, thinking it might have to be a composite shape as opposed to separate triangle, parallelogram, and rectangle.
So I might go tell Michelle right now to just to review. It's all separate and identify 4 separate or 3 separate shapes.
Boys and girls, can you freeze for one moment, please? Take a quick look at your work. Do you have a triangle? How do you know? How many sides? 3 sides. Thanks, John. How about a rectangle? Do we have any rectangles?
Yes.
What can you tell me about parallelogram?
The opposite sides are parallel.
Okay. Make sure you're not doing a composite shape. You don't want them stuck together. We want 3 separate shapes. Okay, put your last little bit of information on your shape, and then we'll see if we can't take a look at a few at the front.
What do you say? You don't need to show any more?
On this specific right angle triangle, I definitely was working from the formula, knowing that I needed my base and my height was going to be divided by 2. So in seeing this in one of the students' work, I would know that they were working from the formula. They understood the formula. Whereas if you look at the triangle here, with the arrows and numbering half a square and a full square, you can tell they're working by the numbers, units. Take a few minutes now to turn to your elbow partner and share what you have on your paper so we can generate some conversation and see what you have that's similar or different and new ideas that you can share with each other.
I drew a square because a square can be a rectangle, but a rectangle cannot be a square. And here I basically wanted just 2 whole ones and then 4 halves because 2 times 1 whole is 2 wholes, and 4 times half a whole is 2, and then I added that up to get 4 units squared. And this one I know is 4 units because I just counted out the units inside the box. I numbered them 1, 2, 3, 4. That's 4 units squared.
So what I did was I drew a square with a length of 2 centimeters and a width of 2 centimeters to get an area of 4 centimeters squared. And these are parallel sides, meaning that they'll never intersect. Then I drew a rectangle with 4 centimeters squared as the area. I multiplied the length and the width to get 4 centimeters squared. And for a parallelogram, I drew a parallelogram with the length as 2 centimeters and the width as 2 centimeters. And then I took off one part of the triangle and converted it to the other side to get an area of 4 centimeters squared.
Great. Do you see anything on Vincent's paper that perhaps is either similar or different than what Allie had on her work?
On Vincent's, he actually has a rectangle, a triangle, and a parallelogram that each have an area of 4 centimeters squared. And Allie's is one shape that has a rectangle, a triangle, and a parallelogram in it with an area of 4 centimeters squared.
Is there anything that you see that Vincent used that's effective math communication that perhaps may not have been in Allie's?
He labeled his sides.
Label the sides, and what did he label the sides with?
Numbers.
Right? So, and those numbers indicate what?
The length and the width of the shape, so you know what he's doing the area for.
Okay. Anybody else have an idea? What else do you see here that perhaps indicates Alex?
He put the formula beside his shapes, where area equals length times width equals 2 times 2 or 1 times 4.
So we see the formulas here. The numbers indicated are the length, width. The measurement units also on Vincent's. Okay.
And if I'm going to draw a parallelogram, I know that this looks like it's going to be two units in length, but in fact I have to count the height, and so I have that in my head when I'm drawing this, and so that I know that it's the height. And some students oftentimes will measure the length of the side rather than the height of the parallelogram, and I find that can be a real problem.
And they could put their base here, for example, and then connect the two sides. So we would have the base equals 1, and the height would be measured like this, as being, I shouldn't say centimeters, I should say units. So the height equals 4 units, and then they could write the area inside as being 1 unit times 4 units, which would give them an area of 4, of course, units squared.
So to draw the shape, I'm hearing you either need to have a rectangle in mind to draw a triangle, or I think you need the formula in mind. So you have to juggle those two things as you're drawing.
Now you're going to talk with your elbow partner and share some of the strategies you're going to use to solve this problem on your own.
First, draw a diagram. Yeah, when I'm going to draw my triangle and parallelogram, I think we better use half squares, and then we can add the halves together to make one whole. And for numbers, we could put the numbers in the shape, 1, 2, and for half, we could just put half.
I noticed that a student over here has 3 shapes,
Yeah.
but is using formulas, and another student over here has all 3 the same shapes, but is counting.
Okay.
I want to use those as your
It'd be
examples.
good to bring those ones up. Okay.
Here's the lesson problem that we're going to give the students, and what do you think of it? I think it would be good if we put it into some sort of context.
Puzzle.
Well,
And it's one of those puzzles in the frame, that they have to put.
You want me to write an L-shaped puzzle?
Yeah.
Instead of using the word frame, perhaps we should use the word like a tray, so the pieces fit on
Yeah,
a tray.
that's right. That's right.
So there are restrictions in terms of perimeter, the
Right.
dimensions of the
Right.
perimeter.
And I don't think we need that actually written in the problem. I think that's something we can just say.
We need to say something about the size of the pieces as well.
So, restrict them?
Restrict them.
Okay.
So what are the sizes of the pieces that they're allowed to use?
Maybe we should kind of work on it.
How should we start? Should we start with, we know that each piece needs 4 square units.
At least.
Okay, boys and girls, this is the problem we're going to work with today. It's our L-shaped puzzle problem. So you have to consider the following things. Your design has to include 3 types of puzzle pieces. It has to have triangles, it has to have rectangles, and it has to have parallelograms. Okay? And when I say parallelograms, I mean parallelograms that have both acute and obtuse angles in them. So we can't use our square and our rectangle. Okay? Each puzzle piece must be at least 4 square units. When you see at least, what does that tell you? At least. Emma?
It has to be 4 or up.
4 or more. Each puzzle piece must have an area that is a whole number. Give me an example of whole numbers. Cameron?
Like 4 square units.
That's an example. 5. Could I use 4.3? No. Could I use 5.5? No. Okay, so it has to be whole numbers. So you're going to think about combinations of puzzle pieces that you might use. See how many solutions you might come up with. All 3. You have to have triangle, you have to have rectangle, you have to have parallelograms there.
Can you use different shapes too?
No, I think they want to keep it just to those 3 types right now. That would be a nice idea for another time.
So like we can't use squares or anything like that. Like
What are we allowed to use? We're allowed to use triangles, rectangles, and parallelograms. We said 1, 2, 3, 4, 5. They're whole numbers. But 1.5, that's not a whole number. Okay?
At least. Whole numbers.
I think they might start with the parallelogram, but I'm thinking that, again, my strategy of doing one for the base, and they could put the other one anywhere they want it, and just see if that would fit. So here's one here, and just keep building the shape up using parallelograms, and then they could redesign the rectangles and the triangles around the shape, knowing that we want to have parallelograms, triangles, and rectangles, and as well, each one has to be at least 4 square units.
Turn to your elbow partner and discuss what is the criteria of this problem. What needs to be done?
So we have to make we have to design a puzzle. Yeah, and it has to have 3 different types. Include 3 types of puzzle pieces, which could be like a rectangle, a triangle, or like a parallelogram. Yeah, and it also says it has to be at least 4 square units per piece. And we can't. And you have to have like a whole unit or centimeter square box. Yeah, it has to be whole numbers. It can't be can't be half there. Yeah. Yeah, exactly.
I've noticed that a few of the students are actually indicating on their rough draft the specific criteria to refer back to. So they're taking what you said and they're writing it down just as a reminder, specifically Ashton. So you might want to ask Ashton to share with the class some of the strategies she's using to make sure she's meeting all of the necessary criteria from the problem.
I'm noticing, Sandra, that the biggest difference that I'm seeing with your students as compared to mine is that they're starting with the parallelogram. I think that understanding of the formula is really strong, where my kids automatically started with a rectangle. That's what they wanted to go with. I wonder if it would change for me, instead of just counting squares, if I actually went to not using grid paper, just giving them plain paper.
In that way, they have to use the formula And knowing that, I agree with you. I noticed that right away compared to your kids that we saw yesterday. I had a feeling that my students would start with the parallelogram first, only because we discussed how the other shapes will work around it.
Second.
What I'm thinking is I might just have them together with their elbow partner discuss just briefly, and then share on the whole.
That's a good idea.
Right. Ayo. Now that you've had the time to individually think about a solution to the problem, I'm going to ask you to turn to your elbow partner, discuss with your elbow partner your strategies to solving the problem and ensuring that you have evidence that you've met the criteria that is on the chart for our problem. If you're looking at the parallelogram, they could start off with that and build around it. I'm wondering what assessment tool we could use as teachers that we could accurately gather information about the children's math communication as well as their math thinking, being one teacher, as you said, in the room.
Yes, to solve, to fill the L shape. What is some information from the problem that you're using to fill the L shape?
Yes.
I noticed that Patrick and Sarah both have all of their criteria that has been listed up for the L shape problem, and they've solved for one L shape. Now they're moving on to trying to use those same pieces in a different way.
Okay.
So they're good.
So when they come to meeting in their group, which is going to happen in the next 30 seconds ago or so, they're probably going to choose their pieces since they met all the criteria.
Right.
Ayo. Hi. Boys and girls, now that you've actually debated in amongst yourselves and decided and convinced each other which puzzle piece happens to be, I guess, the one that's met all the criteria, you're now going to transfer that one puzzle piece onto the larger piece of graph paper. You're now going to take a look and refer back to the communication criteria. When you are referring back to your communication criteria, I want you to think about these questions and how can you share your communication of these questions with your group. The first one is, show your calculation of the area of each puzzle piece. Show how the puzzle pieces cover the entire area of the L shape. Explain how many of each puzzle piece, shape and size, is needed for one puzzle package. And the last one, and that's how you're essentially going to justify that you've met it all. When you explain to me, you'll be explaining how knowing the relationship between the area of a rectangle, triangle, and parallelogram helps you solve this problem. So as you go back to your group right now to recreate the puzzle on bigger chart paper, you need to communicate each of these things following the communication criteria that we've already generated.
The role of the community, the role of your classroom community for mathematical communication. What impact does that have on students expressing their mathematical ideas?
Well, we knew that the rectangle here was more than 4 square units because here there were 4 there, and then there were another 4 up top, and then we knew that 8 square units, which was the total of the rectangle area, was greater than 4 square units. Therefore, we measured the criteria for at least 4 square units.
Okay, what about your other shapes?
Well, the rectangle. With the rectangle, there was 4 square units. And
What was your thought process? What was your thinking? How did you make sure you had evidence to solve this problem?
What we did first was we wrote out our calculations and area A and B, C and D, and E and F. And after we added up our products to get our total sum. All our puzzle pieces are shown up on our L-shaped figure. There are no blank gaps, and they're all more than 4 centimeters squared, unit squared.
Right, Bradley?
What shape did you choose to do first before the rest of your shapes?
We chose to do a parallelogram first because
so it's easier to draw all the other shapes to knowing that the parallelogram's out of our way.
Which shape did you choose next?
Well, we chose the triangles next. They made it a rectangle, so that means it's easier to work with.
So in showing that, did you find some kind of relationship between the shapes?
We found that two triangles beside a parallelogram would make a rectangle.
Any type of triangle?
We chose to do a right angle triangle because it would go all the way to the top of the parallelogram and it would cut it off, and then it would show that we only have the rest of the top of the L-shaped figure left to turn into puzzle pieces for.
Had to do a right angle triangle.
And so that means we would have to do one down here also, and they're both congruent.
Great.
That's basically because a right angle triangle has a base and a height, and it would be easier to find instead of searching for the height. It was right there for us.
In our first group, we had clear answer, and the symbols were shown, and they related the triangle to the parallelogram.
This is our L-shaped puzzle. To start, we used the parallelogram because to us that would be the hardest shape to fit in. And this is our parallelogram here. We have two. And then right after our parallelograms, we decided to do triangles because they just fit into the sides. To find the area of the triangles, we had to dot it out. So we just act like it's a rectangle. Then we divide it by 2. Then we had to do rectangles, and these are our rectangles here.
And looking at this shape, you talked about your triangles there that you dotted out.
These two triangles here are congruent.
Yes.
And so we didn't have to use the formula twice. We just knew right away that once we did one, we knew the answer for the other one.
Their triangles aren't exactly 4 centimeters squared. They have to make it a bit bigger to meet the criteria of this problem.
They do have a parallelogram in there. You see it here, which meets the criteria. Then they do have these two bigger triangles. They had the insight to see that there was another shape in there. However, it's just that it didn't meet that criteria of being 4 centimeters squared. Now, if we had said that this doesn't work there for that parallelogram, how many parallelograms do you actually have in your puzzle piece if we take that one? Okay.
Did the two rectangles meet the criteria? Yes, it did, because the length is 1 and the width is 4, and 1 times 4 is 4, so it's 4 centimeters square.
So we had the formula. Looking at the two, the authors of this solution and the authors of the second one, do you find any similarities in there? Ayo! There we go. Okay, awesome. To sort of share what we've noticed about our solutions and what you've noticed about other people's solutions, okay? And as I'm putting your solutions up, I want you to take a look at some similarities and some differences between all three. And once you've noticed some similarities and some differences between all three, you're going to have some time to discuss in your group. So take a couple seconds on your own and try and identify, just like I'm going to, some similarities and some differences between all three. And now that you've identified some similarities and some differences between all three, I want you to share some of those similarities with your partners in your group. Go ahead, boys and girls. We're going to have recess bell in 2 minutes again. Okay.
Just talk through. That one's the obvious strategy.
Yeah, yeah.
The second one.
But I want them to tell me what that strategy was, though. Yeah. Yeah.
Okay. All right. Why the last one third?
This one should be here, and that one should be there.
You could do that and show.
But
Show me right here. Show it. See the big. It must be bigger. What's really these? What's this telling you about the parallelogram? Looking at the size of these,
right?
You could say it's a bigger parallelogram.
And the minute you have a smaller parallelogram.
Yeah, so you could do that.
Ayo! Good job, boys and girls. All right, so the authors of the first chart paper, all right, are going to explain to us how you chose the pieces. Patrick, do you want to stand up and share with the class, please?
We had to make the figure into, we had to divide it into a rectangle, one face, that's a rectangle, a triangle, and a parallelogram.
So Patrick, let's complete this table here. So what were your dimensions for finding the area of your rectangle?
It was 2 centimeters by 4 centimeters.
And your total area was?
8 centimeters squared.
Okay. And let's finish off with your triangles. And what were your dimensions for your triangles?
4 centimeters.
You have 4 centimeters.
By 4 centimeters.
Okay.
Equals 16.
Okay, so I'm hearing 4 centimeters by 4 centimeters equals, and I just noticed that the formula says divided by 2.
So 4 centimeters times 4 centimeters divided by 2.
Okay.
Would equal 8 centimeters squared. But since the two triangles are congruent, you would multiply it by 2 again, so it'll give a product of 16 centimeters squared.
The authors of the second group, can you guys see any similarities? And I see Sarah, Victoria, Tiana, Jana, and Curtis. Did you guys see any similarities in the strategies the first group used? Which of these two sort of have some similarities and some differences to the first one? Talk amongst yourself for a second, all right? Think on your own and then share with your elbow partner and even in your groups of 4. Go ahead. Claire, what were you saying though about the next two?
They have the same surface area.
Okay.
I'm pretty sure.
You're asking to find the similarities and differences. You might want to refer to the criteria. Looking at the criteria, how are they similar and different? That might be.
Yes. Ayo. So boys and girls, as you're discussing the similarities and the differences between all 3, I want you to think back to the criteria that the companies asked us to take into consideration here in regards to the shapes. And even further, I want you to look at the size. Are you noticing anything interesting between the size of the shapes that each of these three teams here have come up with? Okay? And I like that you already want to share. So take about another 30 seconds with your group and think about those pieces of criteria now. I'm going to ask them now to tell me, and in the end, what I want to guide them is to say that the first and the last, and then we're going to switch them up. Yes. I'd like you to share with us some of the things that you've noticed, the similarities and differences again.
It used more, it separated its L-shaped puzzle into more sections, so it's going to be a little bit more complicated or confusing for them to actually, break it down in piece by piece. But with the other 2 groups, they actually, their sections are bigger, and it's going to be a little bit easier.
I'm wondering now, based on Lucas's observation, if you guys would agree with me that maybe what we should do is sort of rearrange the order of the 3 samples we have up here, okay? And then we'll try and see a few more similarities and differences between all 3. Do you guys agree? Yeah? Okay, so let's do that. What do you notice about the first one and the second one? Some similarities and some differences. Michael?
All the puzzle pieces, they're about the same size.
What pieces are the same size?
The parallelogram and the rectangles look the same to the other one, and they're bigger than the third one, which are smaller.
Wow. And if you were this company, would you want to have more pieces? What do you think? Can you guys talk about that for about 10 seconds? Michael was saying a little bit about the similar size between the parallelograms. Are these parallelograms the same size? Is this parallelogram that we call parallelogram number 1 and parallelogram D, are they the same size, and how do you know?
So I think they're the same size because they both have the same dimensions. So since the formula for the parallelogram is base times height, they both have 4 for the base and 4 for the height. So if they're going to multiply it together, so 4 times 4 is 16, they'll both have a ending product of 16, so therefore they're both equal.
Okay, so you know what? You've justified it using the formula, okay? Now let's go back to the actual group. Let's go back to the authors here, and let's start to document the area onto the chart paper. We're going to move on to the authors of the last chart that we have up here.
We first cut off the side piece and that one, because it looked like it was kind of an odd piece. So, okay. And then we divided that in half, and then we put in the parallelogram. We made a big parallelogram and divided that in half, and then we were left over with 2 triangles and divided those in half.
And what are the dimensions for A?
A is 2 centimeters by 2 centimeters.
2 centimeters by 2 centimeters. Okay, giving us a total area of
4 centimeters squared.
Okay, so what puzzle will the company choose? What puzzle will the company choose, and why?
I would choose Sarah, Victoria, Tiana, Jana, and Curtis's puzzle because they have the most pieces, and it'd be more difficult for someone to solve a puzzle that has more pieces instead of the ones that have 4 or 5.
More pieces? Okay. All right.
It would really depend, what kind of toy company it is, because if it's for, little kids, I would probably pick either the first 2, and if it's for, more advanced, kindergarten, I would pick Sarah and Curtis's and Tiana and Jana's group, because then it would be more challenging for them.
Okay, so we definitely have an audience that we need to make sure we know what type of puzzle goes to what audience. Now, what is it about this piece that the company would really, really, really pay attention to?
There's more combinations that make the L-shape puzzle.
Multiple combinations?
Yeah, and there's more variety of how to make it, so you can mix them all up, and it's not all the same. It doesn't have to go that way. You can make it in different ways, and I think that's better.
Okay, so multiple combinations?
Yeah.
All right. And as a company, you would want that?
Yeah.
For your audience? Okay.
People don't want a really, really easy one. They want one more challenging.
Is there anything else after we look back at the very beginning? Okay? We take a look at where we've come from now. We got to look back to where we've come from. And what was this company asking us to do?
If you go to the checklist, 4 square units, it has to be 4 square units, and they have rectangles and parallelograms and triangles.
Okay, so they met the criteria?
Yeah.
Anything else? Michael?
They've also included that they're all whole numbers, not having fractions at the end.
The math communication with the pitches, numbers, words, and symbols.
So the minute you see pictures or meaningful symbols or meaningful numbers or meaningful words, you raise your hand to show me that you can see that in that final one here. And there are elements of all of those things in each of these charts.
So let's take a minute and I'd like you to take a careful look at the solutions. Maybe pick 1 or 2 solutions. And I'd like you to try to look for the mathematics that are in those solutions. So what mathematics do you see in the solutions? We can look across solutions as well, so we can compare solutions. what exists in one solution that might not exist in another one, or what are the similarities between the solutions? So we're going to list out some of the mathematics that we noticed.
This group seemed to count each of the squares and the half squares to get the area, and this group actually looks like they used the formula because they've drawn a line to show the height of the triangle, and they used the formula to get the area.
So Michael, what you noticed is that some students are measuring the area. And they're doing that by counting. And some students are calculating. The area. And what are they doing what are they using? They're using the formula. All right. So what other mathematics are we noticing? Similarities, differences, that sort of thing.
What they did is that they really wanted to turn that irregular figure into two quadrilaterals, or two rectangles in this case. So if you notice, forget about the lettering in that case. What they did was that they started off in separating into two rectangles, two familiar shapes that they know the formula for finding the surface area, and then moved into trying to make it into a more complex puzzle by separating the square to create two rectangles. And then from there, they moved on to one triangle, which gave them the frame to create the parallelogram, and then filled in the last triangle. And if you move on to the next one, which was the order we used this one for the band show, the order that they labeled them according to letters was the order they actually placed them into the puzzle. So A and B, they pulled that away to create two rectangles. So we moved away from our irregular shape. So they've done that, they've separated it, and then they've made one rectangle into two squares to increase the number of pieces, to increase the complexity of the puzzle. And then they've moved on to C and D, one big parallelogram. No, let's make it more complex. Let's separate it into two because it's met the criteria of at least 4 square units.
Because you see the students beginning with the parallelogram and then filling in to create a rectangle by adding triangles, you see that they see the relationship between the parallelogram, the triangle, and the rectangle.
Most of the kids separated either this portion of the L off or this portion of the L off, except for this group who separated up here but still had an irregular shape. Most of them make it a regular shape, except for that one.
Most decompose the L into two quadrilaterals.
Yeah, they put two parallelograms together, but they still have the triangle on each side. I noticed in this one it seems to be two parallelograms, and then they have two large triangles on each side. So they just have it side by side.
So in the other solutions, there may be more than one parallelograms, but they're all of the same area. This one is different in that way.
We determined earlier when we were working on the problem that the maximum number of shapes, or the maximum number of figures that we can decompose the L into is 10. Did any of your students, do you notice any of your students who picked up on that?
Yeah, the top right. Yeah. Top right has 10.
So moving from perhaps more familiar shapes to more complex shapes. Interesting.
Well, you can really see symmetry in some of the solutions, such as that one in the top right, beside that.
Okay, this one.
And also the one in the bottom left is actually quite similar in a way to that one.
Symmetry right down. I'm wondering, do students understand the relationship between counting to find an area and using the formula to find an area?
I think that that some of the students don't. I think that some of the students, for instance, if you have this here, some of the students are simply going 1, 2, 3, 4, 5, 6, 7, 8. I think that's one strategy. They're just counting squares. I think some might realize that there are 2 rows here, and 3 columns.
4 columns.
Oh, thank you, 4 columns. And I think they're seeing that as 8 square units. I think they also, some of them are noticing that there's linear dimensions here as well. So here's 2 linear dimensions. And then here, you've got 4 linear dimensions. So I think they need to go from the counting to the rows and columns and then to the linear dimensions. I think we need to bridge that for them.
Problems are intriguing to students and engaging for students for different reasons. Sometimes it's the context that is intriguing. Sometimes it's the numbers themselves. For example, when we're looking for patterns that seem unusual to us, these are the kinds of things that will engage students in really exciting conversations.
You need to start with a good problem, a problem that requires kids to debate and deliberate and to try to convince each other of their work and their solution to the problem. When students are solving challenging problems, truly perplexing problems where there's no clearly evident solution or immediately evident solution, and students have an opportunity to share their thinking with each other while they're solving the problem, that's, I think, the start of a vibrant math community.
Well, I think when you walk into a classroom where children are learning mathematics, you see the students engaged in the learning. You see an environment where students are free to take risks. By the students sharing the responses, then other students can build on that and we can build an answer together. So I think having the students comfortable celebrating successes in the classroom as well. When you walk into the classroom, you would see evidence of math.
There was math everywhere. There's math on the ceiling, there's math on the walls, there's math in their immediate, on their desks, there's math on the shelves, there's math everywhere. So already just when you walk in, your visual screams math. And it's not just a wallpaper, it's not just decoration. If you were to ask every single student, they could tell you what every single piece of math means in that classroom because it's not just there for decoration. You would hear reference to what's around the classroom. You would hear the words on the ceiling. You would hear the strategies that they're using.
They are involved in their own learning. They claim responsibility for generating ideas amongst each other, sharing ideas, and accepting each other's ideas, and understanding that everyone has a valuable contribution.
And I think when students start learning that way and communicating that way from a really young age, so it's part of their everyday, they do it every single day, it just becomes part of your math community. Like, that's what they expect to do.
I think the challenge lies in having children not think that they have to give you the right answer right off the bat. Sometimes they have this sense of wanting to please the teacher, so they have a fear of not telling you right away what they're thinking because they want it to be accurate. So establishing in them that sometimes making a mistake enables you to learn it better so you can remember and then be able to explain it more to yourself and to others around you.
If a classroom is a math community, the teacher's language should reflect that. So when a class is looking at a solution, the teacher shouldn't say something like, convince me. The teacher should say, well, does this solution convince us? Are we convinced with this solution? It becomes the community's responsibility to support or to challenge the ideas that are presented. Authority doesn't rest solely with the teacher. The authority rests with the class.
A strong community is reflective of the trust that exists between all the members of the community. And it's a place where students feel secure in sharing their ideas, taking risks by exploring new ideas, and also where students learn from each other in listening to each other's responses. A teacher might model for students how he or she validates the responses of all the learners. So they will include the responses in the conversation that the community is engaging in. The teacher might model how one group's or one student's solution is used to build upon the ideas of others, and how no matter what the solution is, it is useful in the learning of all.
I think allowing for think time is a big thing. You can't pose a problem and expect an immediate answer. You have to give them an opportunity to think about it. Now that can be just independently for overnight. We're going to look at this tomorrow, think about it, we'll come back and talk about it later. Or maybe it's just a few minutes to themselves and then sharing with a partner and then moving to a slightly larger group, but always coming back to a whole group in the end. So you can kind of piece everything together and give everyone a full picture of the big idea.
I think with mathematical thinking, they need to know how to explain how they got to their answer. And sometimes that doesn't come easily to them. So by giving them tools, such as vocabulary, and myself being a model with the math language, so they're used to how to explain certain aspects of a certain concept that we're discussing, that they feel more comfortable and they're able to make the connection between this is my answer and this is how I got there.
Before I give the lesson, or before we talk about it, I have to cement the language into my vocabulary so that they get it right the first time, rather than saying it wrong and then having to go back and say, no, this is what you were supposed to say. It's not a side, it's a face. And then they don't have that language up front that's wrong.
So accurate, precise language being modeled before.
Right, so that takes me, I have to think about that before.
They don't realize what the purpose is in communicating, and sometimes they think it's just for the teacher, but really it's for the whole community to sort of understand better. So as a result, that whole idea of pictures, numbers, and words, and they're trying to be so precise and make sure they have a picture for something and the words to correspond, and they're just putting pictures that are erroneous and have nothing to do with the communication. I think sometimes those things get in the way of what we really want them to do.
We need to take another step, though, and that is to ensure that the solutions that students are communicating are convincing, that their reasoning is clear. So they're not just doing the work and showing their work, they're using what they've done to formulate a convincing argument.
We used a gallery walk in my classroom so that each group worked on a solution to the problem, and then they were allowed time to go and visit the other tables.
And it really gets them to see a repertoire of styles and approaches. And hopefully, having seen that, they can adopt some of those for their own work later on. And then when you get to a whole group, you can kind of validate the work that everyone has done, and as a class, you've come up with a really good piece of evidence.
Myself, along with the co-teachers, when they were working on their problem together in their groups, we rotated around to see how they came about to get their communication displayed on their chart paper, and what strategies they were using. And the focus was math communication. There was a criteria that we talked about before, that it was clear and precise, and they had symbols, and it was accurate, and they had formulas, diagrams to best defend their solution to the problem and make evidence to the rest of the class that they were exactly, covering all the criteria that was specified on the problem. And during the Math Congress, I put three groups went up, and we pointed out the similarities and the differences that they had for their solution.
I think the Math Congress is a way of establishing the children to stand in front of their peers and defend their answers. Not only does the group who's presenting come up and show some of their strategies, but the children, the audience themselves, the other members of the class, are able to look at the work and find differences, similarities, strengths, and where to build on those strengths, and maybe find different approaches that they may not have been aware of, and show amongst themselves that there's more than one way to get to our answer. I work with a team of teachers, and before we pose a problem to our class, collaboratively we get together and we look at, okay, what are the possible solutions and what do we want the children to learn from this? So before we approach a problem, we already have in mind a focus, what we want the children to learn. And that helps. And when I'm rotating around the room, in what group would I want to come up and present? The curriculum expectations are one of our main focuses when we're looking at what our focus is for the children to learn. We want to make sure that we've established what it is through the curriculum that the children need to have. I rotate around the room and I find groups that have established a certain way of presenting their problem, maybe problems that they could build on each other, or I find a totally different approach that perhaps I never even thought of, and put it up on the board. And the children themselves have to analyze how they got to that solution. When we first started out, it was a challenge for them to understand themselves how to ask the question. But with each practice that we have, their questions become more and more analytical. They know what we're looking for because they've generated amongst themselves what is good communication. So they have established already what they're looking for.
After students have had a chance to solve the problem, and when the teacher is helping students to share the problem, and there's that discourse and the tossing around of ideas in the classroom, that's when the mathematical community in the classroom really takes off. All ideas are valued. All ideas are put to the test of the classroom. So the audience is the classroom, and mathematical ideas have to stand like the test of the classroom. If there's an idea that's presented that might not be complete, a member of the community can question that and say, hey, wait a minute, I'm not so sure about this. And then the person who presented, or the student who presented the answer, has to work at justifying that and reasoning. And if they're not able to do it on their own, there are other community members who can jump in and help. So a mathematics community truly lives in the discourse between students, but also it lives in the discourse between the teacher and the students, the discourse that the teacher facilitates with the students.
Well, we used Bancho to share our solutions, and we started off with the parallelogram as the most obvious shape in the puzzle pieces. So we started from there, and we moved on to more pieces, and we started comparing similar shapes, similar sizes, and from there moved on to the chart paper where we could identify the formulas they used to identify the total surface area per shape.
When students are sharing their work, let's say in front of the whole class, for the teacher to annotate that work, to pull out the key terminology, to highlight certain words or certain symbols or certain conventions that the teacher would like the students to be using when they're communicating on their own. So what we hope happens is that the students are sharing these ideas between themselves. They're sharing these ideas during a consolidation phase of a math lesson, and then they're incorporating what they've learned into the next problem that they may try to solve and communicate their solution for.
I think one of the most important things that makes a family of schools or a group of teachers a mathematics learning community is a genuine enthusiasm for math and interest. They want to know what it is about the math that they need to engage the students in, and they're constantly asking questions and using that inquiry model themselves to figure out the answers. And solving the problems together as a group of adults, I think, is really important. I find it really invaluable to bounce ideas off other people, to say, you know what, I'm thinking about this way of solving this problem. What do you think about that? And oh, I never realized about that. You know, you don't have to have pairs of parallel lines. You know, like things that we talked about. I think it's. I think one idea leads to another idea, and if one person's enthusiastic and asking the deeper questions, then that's going to lead the community to do the same.
A mathematics learning community is a classroom where everybody is learning. So it's not just the students who are learning, it is the teachers also. So you can't just sit back and passively hope to soak things up. Everybody has to be active. And I think that's why I'm so excited about this co-teaching, because teachers are learning from the students, and teachers are learning from each other. They're teaching a lesson one day, one teacher's teaching it, and then sharing her work with her peers, and then her partner is teaching it the next day, and they're comparing the work that they get, and so everyone has an opportunity to learn.
In co-teaching, you've got two minds working on the same lesson, presenting the same lesson, presenting the same problem to students. Having the second co-teacher in the classroom provides you with an extra set of eyes. So an extra set of eyes observing the student work, looking for interesting strategies that students are using, looking for significant leaps in the strategies that students are using, looking for misconceptions. A co-teacher can point that out to the regular classroom teacher and help the teacher to highlight some of those things during the lesson. A positive experience is just being able to discuss as the lesson is going the direction that the lesson should take. So in co-teaching, you start out with a lesson plan. But as we all know, lesson plans don't always go according to what you would like. When you encounter a challenge or a difficulty, the co-teachers are able to share their thoughts and problem solve, on the spot, the direction that the lesson should take. To prepare myself for a co-teaching experience, I find that I need to dig into the math myself. So if there's a problem, I need to do that problem by myself. I also need to take a next step, and that's to talk about the problem with somebody else. So essentially sharing my solution with somebody else and saying, are we on the same track? Are we on different tracks? Oftentimes, another teacher, the co-teacher, will have a different perspective on the math. And I find that that enriches my understanding. In the co-teaching situation, after students are given a problem and they're solving their problem, now I've got a whole other array of solutions to look at. And those, once again, add another layer to my understanding of the mathematics often. So, looking at the solutions that students have generated, going over to the other teacher, discussing those solutions. Is this lesson headed in the direction that we had anticipated? Is it taking on a different direction? And making a decision about the direction to move on from there.
If we can promote that co-teaching environment, then there are more ears and eyes all over the classroom.
And the next step with co-teaching, I think you need to understand who is the main teacher in the classroom, and then what is the role of the co-teacher and how the two are going to relate together. And you have to be clear on the expectations and what it is that you're looking for.
Well, I think the most important thing is making sure that it happens. Finding time and making sure that everybody on staff knows how much we value it. And it hasn't been difficult because the enthusiasm from this original group of teachers is spreading. And so we can tap into that, but I think we need to be really supportive in planning what goes on in our school so that we can allow it to happen, allow them to work together, to teach together, to plan together, and to share that with other teachers in the school. The three of the teachers who are co-teaching right now were working together in the library, and they had student work spread everywhere. They were looking for similarities, for differences, for misconceptions, for things that they needed to work on for the next day's lesson. It's important. They know that I'm a part of this math study group, and there are other teachers, other administrators from other schools who are involved, and they know that we value it and that we're learning, and it's an important part of our school culture now. So, and we're not just modeling it, we're living it.
We have times when teachers can get together and plan. Some of our times the area of focus is math, sometimes it's language arts. But I think you have to intentionally build that into your planning time with the teachers. We have teachers come together by divisions. We have times when they come together by grade levels, and we have times when we build into the day blocks of times where teachers are off at the same time so that they can share ideas and go into each other's classrooms and co-teach or do some of the other things that we're encouraging them to do.
I think one of the challenges is that often as adults and as teachers we have so much to do, and sometimes it's difficult to pause and to dig deeper because we're so interested in getting things done day to day, and we want a quick answer to things and we want to move on. And I think when you're developing these communities with adults, you need to be a lot more reflective than you usually are in your day-to-day life, and you have to kind of put yourself on hold and say, okay, for the next 45 minutes, let's really investigate this. Let's inquire about this, and I wonder how we would answer this question. I wonder how the students in our class are going to answer it.
The biggest challenge that we hear all the time is the one of time, and having teachers making sure that they put time in their lesson to get to the point where students are able to justify. And sometimes, due to the constraints of the school day, teachers have trouble getting to the end part, which is the most valuable part, where the students are explaining their thinking or justifying or going on a gallery walk and taking it to that deeper level. So it's important for the teachers to know that the three-part lesson, the third part of the lesson, is one of the most critical components, and to make sure that we allow time for that. And as a school administrator, I tried to do that by allowing teachers large blocks of time for math. It's always an issue, you never have enough time, but we just have to make it a focus and make sure that there's as few interruptions during the school day so that the students do have large blocks of time in which to work and solve their problems.
As described in several ministry documents, such as the Ontario Curriculum, Mathematics Grades 1 to 8, the Primary and Junior Expert Panel Reports, and the Guides to Effective Instruction in Mathematics, effective mathematics teaching and learning in Ontario focuses on developing students' mathematical thinking, understanding proficiency in using procedures and strategies, and communication through problem-solving based lessons. By learning to solve problems and by learning through problem solving, students are given numerous opportunities to connect mathematical ideas and to develop conceptual understanding. Problem solving allows students to reason, communicate ideas, make connections, and apply knowledge and skills. Problem solving promotes the collaborative sharing of ideas and strategies and promotes talking about mathematics.
Ashton. So you might want to ask Ashton to share with the class some of the strategies she's using.
A key aspect of a problem-solving based lesson is the teacher's coordination of students' sharing of their solutions for learning and consolidation.
According to the Guide to Effective Instruction, K-6, Problem Solving and Communication, class discussions provide students with the opportunity to ask questions of one another, to make conjectures, to share ideas, to test and clarify those ideas, to suggest strategies, and to explain their reasoning. In hearing the ideas of their peers, students learn, with the guidance of the teacher, to discriminate between effective and ineffective strategies for problem solving. Dr. Kathy Bruce from Trent University explained that the dynamic negotiation of mathematical discussion requires the teacher to possess facilitation skills and heightened attention to classroom dynamics. In a mathematics learning community, students are expected to justify and explain their solutions so that they are extending their own thinking as well as the thinking of others. Dr. Kathy Bruce explained that student interaction is an essential aspect of effective mathematics teaching. If students are left to their own devices, they will not necessarily engage in high-quality math talk. The teacher plays an important role.
Student talk is one of the most effective ways for students to demonstrate and to improve their understanding. However, listening to the responses of others and articulating understanding are skills that take practice. Students need many opportunities in the classroom to help develop these skills. Another significant aspect of mathematics learning includes students' representation of mathematical ideas and relationships and modeling of situations using concrete materials, pictures, diagrams, graphs, tables, numbers, words, and symbols. Learning the various forms of representation helps students to understand mathematical concepts and relationships, communicate their thinking, arguments and understandings, recognize those connections among related mathematical concepts, and use mathematics to model and interpret realistic problem situations. When students share their thinking processes, the teacher gains deeper access to what they understand and valuable information that can be used to inform instructional decisions.
High-yield mathematics instructional strategies address the observations and suggested strategies for improvement described in EQAO's provincial report so that students will learn to provide a complete explanation and/or justification using mathematical terms, to practice orally and in writing the use of mathematical language to explain mathematical processes and applications, different ways to solve multi-step problems, appropriate problem-solving strategies.
Thank you for joining us for our numeracy webcast, High-Yield Strategies for Improving Mathematics Instruction and Student Learning. You have experienced some strategies for studying and improving students' mathematical thinking and communication during a problem-solving based lesson or a numeracy learning block. We play this webcast in its entirety to activate collaborative professional discussion and inquiry about improving mathematics instruction and student learning, or select one aspect of this webcast to study further. Try to implement any of the mathematical instructional strategies illustrated during the webcast within your classrooms. Use a job-embedded professional learning framework like co-teaching or teacher inquiry study to enable you and your colleagues to investigate ways to improve your knowledge of mathematics for teaching, mathematics instruction, and student learning and achievement of mathematics. Visit www.curriculum.org for a complete listing of archived and upcoming webcasts.
Well done, ladies and gentlemen. Thank you very much.
So, having done all this, guess what? You're
great, fantastic, unbelievable, all day long. Woo!
Math is so